So third speaker of the session, we have Víctor Muñoz Villarragut from the Polytechnical University of Madrid, and he's going to talk about asymptotic behavior of a neural network with infinite delay and Heavyside operator. Please, Víctor.
Okay, thank you very much. I would like to thank you for giving me the opportunity to give a talk at this conference. This is a joint work with Peter Kleden, who right now is at the University of Tübingen. And I'm going to tell you about a system of about a neural network defined by means of a Heavyside signal function and its approximation by means of smooth functions. Okay. First, allow me to introduce a little bit of the model. So we have a system of n neurons sending signals to one another, and these signals increase or decrease the potential, the electrical potential within the neurons. The aim of these systems of equations is to study the time variation of the potential within the neurons. So I'm going to introduce the equation term by term so that it will be hopefully clear. The potential for the neuron number I, let's say, will be x sub I. And we're going to study its variation with time. This variation decays exponentially if there is no signal coming to the neurons. So we'll have a term accounting for that exponential decay. Then, if we take into account the signals coming from other neurons, say neuron K, and there will be many Ks like that, we will have first a signal, a signal accounting for some decay in the potential. This is proportional to the history of the potential of the emitting neuron, the neuron emitting the signal, okay? And it will depend on all the history of that potential. So it has an infinite delay. We have represented this in the most general form we can choose, which is by means of a Borel measure. This way we can take into account atomic delays, finite delays, and infinite delays. Well, not all kinds of delays will be included, but we will talk about that a little bit later. Also, some signals come from neuron K to I, okay, and we will have a coupling strength, which is an influence that neuron K has over neuron I, depending also on the history of the potential of neuron K and also on some coefficient, which will be positive or negative. So this term can increase or decrease the electrical potential within neuron I. Finally, we have a term of external stimuli, which come to I, and they are non-autonomous. I mean, they are not constant. About function chi, this function chi here and here, okay? We will speak a little bit later because there are several choices that are interesting, and we will make several of them also. As for the variation of the coupling strength is given by an exponential decay, as before, and it is given by Hebb's law. Hebb's law says that there is a term like this, also depending on the history of the potential of the receiving neuron, no, the emitting neuron, sorry, and on the potential of the receiving neuron. This sign, super plus, means that this number is the number itself. It is if it is positive, and it is 0 if the number is negative. Okay, so we have this system of equations. Notice that we have n equations here and n times n minus 1 equations here. it adds up to n squared equations. So what signal operators are we interested in? I am referring to this function chi here. Yeah? It's the kind of neural system that we are studying. Well, one possible choice is to choose a sigmoidal function, which is given by a logistic function, which is smooth and depends on a parameter epsilon, which controls the slope here. Another possible choice is the Heavyside function. We have formulated it as a set-valued function to introduce some formalism that will be useful in the remainder of the talk. And so we will define it naturally as the singleton 0 for negative values, the singleton 1 for positive values, and the interval 0, 1 if the argument equals 0. And we are the aim of the talk is to approximate the asymptotic behavior of neural networks defined by means of the Heavyside function with those defined by means of the sigmoidal function. To do so, we introduce a third type of signal operator, which is in between these two. So it is defined, well, it is the blue function, okay? So it is defined starting from the sigmoidal function, and it just covers it with boxes. So to say, in such a way that it resembles a lot the Heavyside function. It is defined as you see, depending on a parameter epsilon. So we have a family actually of neural networks, and this function B is a strictly increasing function, continuous, and it vanishes at 0. Okay, so well, we have these three families. Well, these three neural networks. Well, there is a catch to this approach, which is that in the cases of the Heavyside function and the inflated, I will call this blue function an inflated signal, okay? In these two cases, we have a set-valued function, and instead of a differential equation, we get a differential inclusion. The only difference being that there is belonging to sign here. And actually, we will infer all the properties of the solutions from the properties of these sets on the right-hand side for the Heavyside and the inflated systems. Okay, another point of interest is what does these integrals here mean when we have a set-valued function inside? Well, in the case of the sigmoidal signal operator, we have integrals with respect to regular Borel measures, positive measures, okay? So it is something usual. But in the case of the Heavyside and inflated signal operators, we have integrals of a set-valued function. And so we have to introduce Aumann's integral, okay? Aumann's integral are integrals of set-valued functions, and they are defined for set-valued function as the integral of all the selectors of the set-valued function. A selector is just a function which happens to take values in the image of the set-valued function, okay? So with this meaning, we have well defined this system of equations. Well, let us speak about the phase space we're going to work on. And first, a little bit of notation. We will denote by Rn squared the set of x of I, z, I, j, which there is one component for each of the equations or the inclusions we have talked about. And we will drop the indices as much as we can so that we will keep it clean and simple. And we will consider the Banach space of C gamma, okay, given by continuous functions from -infinity 0 into Rn2. And such that the weighted limit by means of an exponential at -infinity exists. we will endow it with the norm given by the supremum of those values in norm, okay? This space is interesting because this topology of finite space is equivalent to that of the continuous functions from -1, 0 into Rn2, and there we have Arcelà-Scully. So that's why the choice of this space is so interesting. Well, we will make some initial hypotheses on our system. They are essentially the following ones. The exponential decay terms are locally Lipschitz continuous, and they are separated away from 0, okay? In the sense that you see here. Also, the integrals of the exponentials take into account that t is negative, so this gets quite big, are finite. So we cannot choose infinite delay in general for our models, but we can use some infinite delays, all finite delays, and all atomic delays. So we're covering most of the cases of interest, all we can. We could not relax this anymore. And we will also assume that the external stimuli are continuous. They depend on time, if you remember, and we ask that they are continuous. So let's do a brief incursion into the sigmoidal system of equations, which are the system of equations that we are going to use to approximate the Heavyside ones, okay? Well, there are standard results, as you can see in Hino, Murakami, and Naito, saying that, it is easy to check that the function defining the equations and the inclusions are continuous and unbounded sets. And so we have local existence of solutions for the initial value problems. Actually, we can prove that they are Lipschitz continuous unbounded sets. So actually we have uniqueness, and so we have local existence and uniqueness. Moreover, we can prove this kind of a result, which says that for a finite amount of time, we can bound the size of the history of the solutions, which we are denoting as is usual by u sub t, the history up to time t, by an exponential. This means that it doesn't blow up. And so we have the following result. This is some sort of Grunwald's lemma, but adapted to the current situation. So we have global existence, okay, for all epsilon, and we are talking about the sigmoidal systems. So we have global existence and uniqueness. So far, this is the only thing we need for the sigmoidal systems. So let's go and talk about the Heavyside systems, which are the ones we are most interested in this work. And let's make a small detour. Let's talk about the properties of Aumann's integral, because it is defined in terms of regular integrals, but actually it's a set. So we'd like to know some properties which are not so typical of integrals, as whether they are convex. Not in general, actually they are not convex for non-atomic for atomic measures. But in our case, we don't have any integrals. We have these very specific integrals, and they are convex in R, okay? So they are convex subset of R or an interval, okay? And does it work well with limits? Yes, in the case we are interested, if we move the parameter epsilon and we make it decrease to a fixed parameter, then the integrals converge. Here, d sub h is the pseudometric of Hausdorff, okay? Likewise, we can, if we have a sequence of functions here pi is any projection from Rn2 into R, then we get the same convergence. So they work very well. These two results allow us to prove well, to end the detour actually, and to prove the convergence theorem. This is one of the main results. So actually we have a fixed time, converging parameters, converging initial data, all bounded by a fixed constant. Then, if we are given, and we are talking about the inflated systems, if we are given a sequence of solutions of the inflated systems, then we can find a subsequence converging to a continuous function, which is a solution of the limit equation, the epsilon-0 inflated system. Okay. What does it matter? Okay, so first, the corollary is what we are going to use actually. So if we have a fixed parameter, say epsilon naught, like this, and a sequence epsilon sub m convergent to it, we can use the solutions of the sigmoidal system, which trivially are solutions of the inflated system, and we get a solution of the limit inflated system. So we have existence of solutions for the inflated system, okay? But actually what happens if we write here, instead of epsilon-0, we have a 0? Well, then we have existence for the Heavyside system. So it's the same argument, okay? We take solutions of the sigmoidal system and we can approximate by means of a subsequence a solution of the Heavyside system. But there is something which is not that nice, which is that we don't have any uniqueness for the solutions. And this is due to the fact that we are using set value functions, and there is much freedom when it comes to the behavior at 0 or around 0 if we are talking about inflated systems. Well, finally, let me talk about the asymptotic behavior. The attainability set is the set of values which are reached by means of a solution of the many solutions for the inflated or Heavyside systems from t0, u0 to time t. There might be several values, and that set is called the attainability set. It has several useful properties. It is a set valued process. It is upper semi-continuous and asymptotically upper semi-compact for small gamma. Gamma, remember, is the constant defining the phase space. Then, if we consider a universe of the universe of non-autonomous, non-empty enclosed subsets of C gamma with a uniform bound, that is, we have closed sets, and there is a bound which a fixed bound which is valid for all times. Then, and with an additional hypothesis, which can be greatly generalized, but I have written a simplified version here, so that it is easier to read, and it depends on the parameters of the original equation. Then we can prove that there exists an absorbing set, okay? And if they're using a result of Tomás Caraballo and Peter Kleden, we can prove that the set valued process has a unique pullback attractor, okay? With respect to the universe T. As for the sigmoidal system, it defines a non-autonomous process. This is simple, actually. It's much more simple than the one we were talking about before. And as before, we can prove the same theorem. It has a unique pullback attractor with respect to the universe T. We would like to compare these attractors. So far, we have the attractors for the attractor for the sigmoidal system, for the inflated system, and for the Heavyside system. Okay, and taking into account the inclusions that we had before, the attractor for the sigmoidal system is included in the one for the inflated system, and the one of the Heavyside system is included in the one of the inflated system as well. But we would like to compare the Heavyside attractor with the sigmoidal attractor. So actually, we can prove the following theorem: that the Hausdorff distance in the phase space, C gamma, converges to 0 when we approach the Heavyside system, with the inflated attractor, the Heavyside attractor, sorry, with inflated attractor. But moreover, the sigmoidal attractors also converge in terms of this Hausdorff metric to the Heavyside attractor. And this is what we wanted to prove. We have been able to approximate the Heavyside attractor by means of the sigmoidal attractor. And that's all. Thank you very much.